So we can see that the operating system actually have to keep track of so many things. Okay, it has to keep track of the processes. It have to keep track the IO devices the processor using. It have to keep track of the main memory. Okay, it has to keep track of everything. So the operating system actually needs a structure so that it can actually keep track of all the processes that are being used, the way which resource it is using, which state it is in, and so on. So that's why the operating system use a structure, a control structure named process system control structure. So what is the purpose of this? The reason is that the OS must have information about the current status of each process and resources. So which resources it is using, what is the current status of the resources. OS constructs and maintains tables of information about each entity and its managing. So basically what OS does, it actually does all this too. So what are the tables the OS have? OS basically have this 4 table: memory table, IO table, file table, and the process table. Now before going further, so if anyone want to take a namaz break, you can just leave. Okay, the topics are very straightforward, and if you don't understand later, you can ask me now. But if you want to go to namaz, you can actually leave now. So now, as I was saying, that we have this basic 4 type of table: memory table, IO table, file table. What it does, the memory table actually, as you can understand from the definition, it keeps track of all the memory. It can be a main memory, it can be a secondary memory. So it keeps tracks of all the memory. Secondary, some of the main memory is reserved for use by operating system. Now, you know, operating system actually itself is a software, right? It has different components. In the chapter 1, we have seen the components, like it has first it has a kernel, then it has some graphical user interface, the device drivers, and so on. So all those softwares are itself are a program. So operating system reserves a special part for itself so that it can work properly. The remainder is available for users by the process. So let's assume that you have a 8 GB memory, 8 GB RAM. So out of that 8 GB, might be 2 GB is reserved for operating system. Then processes are maintained on secondary memory using some sort of virtual memory or simple swapping mechanism. So we have told you about that. We will discuss about this swapping mechanism and virtual memory in the upcoming chapters. Okay, an allocation of memory, memory table must include the following information: allocation of main memory to process. So out of the, let's 8 GB of memory, which part of the memory has been allocated to the process? Like it might happen this 500 megabyte has been allocated to the process. Allocation of secondary memory, like in your hard disk, which space has been allocated for this process? Any protection attributes of blocks, so whether that memory is free for all, or it can be shared, or it's very personal. For example, if I talk about the memory of YouTube, so the videos in the YouTube, you will see that there are 3 types of video in the YouTube. One is public, that you can just search and you can see. So that type of memory is available to everyone. Okay, there is no protection given. Another memory is private, so you can only see it if you have the link. Okay, no, you can, private means only you can see it, and unlisted means you can see it only if you have the link. And also any information needed to manage a virtual memory. So these are different types of memory table. And then we have the IO table. As you can see from the name, it store information related to the IO operation, the status of the IO operation, like what input you should take, from which keyboard or mouse you should take, and so on. Then we have file table. We use the file table to provide the information existing file, like what files you have in your computer. So if you just go to the file manager, okay, you can see, if you open the file manager, you see the local C, D, and from the C drive, you can actually, how should I put it? Like you can see what are the programs you have installed in your C drive and so on, their current status, the location of the secondary memory, and so on. Okay, and then we have in other operating system, so much of the detail of the file management is managed by the OS itself. So we don't actually have to worry about how the file is stored or moved or deleted. Okay, we just copy paste and we just remove it. So we just focus on the basic things using the file. We don't focus on how the file is stored, okay, which memory it is stored. That is done by the operating system. Then we have the process table. So this one is a little bit in details. Process table, operating system must maintain process table to manage process. So the process table, first of all, it has two additional points it has to make. There must be some reference to the resources such as memory, IO files. So each process must have some reference to the resource. So process ta kon dhoroner resource use korche, IO files, we all have to be mentioned. And then how does the OS know to create the tables in the first place? So if we go here, so first we have to know where the process is located and the attributes of the process that are necessary for the management. So if this feels confusing, let's just go to the process typical elements. So what are the elements that are in the process? The user data, user program, system stack, and process control block. So these four type of information are in the process image. And then how we store this information? As you can see, this is the first part. We store process identification. So what does identification mean? Process identifier of this process, identifier of the process that created the process, parent process in short, user identifier, who is actually using the computer. Second part, process state information. So what registers the process is using, what are the data of those registers, what stack pointers, control and status registers is using. So all those information are stored. Third, process control information. To control the process, which state the process is in, what is the priority of the process, which scheduling related information it is storing, the event and the data structuring, the IPC, the inter-process communication, and finally the process privileges and process management. And last, we have this, finally, the PCB, process control block, as you can see from here. So all this information are stored in the process image, okay? So these are two parts, as if you can see here. So these attributes, we have process identification, process state information, and process control information. These are grouped into three: process identifier, process state information, and process control information. By combining all these three, we have the process attributes. So this is part two. And what was the part one? Part one was process location. Okay, so if I go back again, so again we're talking about process table. The process table actually maintains the information of the processes. Process table actually needs two things. First of all, the location of the process. Secondly, the attributes of the process. So what is the location of the process? So the location of the process means, in simplest term, what memory it is using. So in your computer's memory hard disk, where it is, that is the process location. And what is process attribute? The process attribute is actually three things, the combination of these three categories of information, and each category contains this information. So this is all about process image. And finally, we have some rules for the PCB. What is the rule? That PCB is the most important data structure in operating system. It contains all the information about a process that is needed by the OS. Blocks are read or modified by the virtual every module in the operating system. PCB defines the state of the operating system. So all this important information are stored in the PCB. So that's why it is actually very important. Secondly, difficulty is not an access but protection. A bug in a single routine, such as interrupt handler, could damage PCB, okay, which could destroy the system ability to manage that affected process. So if there is a bug in a single routine, okay, such as interrupt handler, it could actually spread throughout the PCBs and contain some damage. So protection is very important. Maybe it come from virus, or it might come from other sources. And finally, these problems can be addressed by requiring all routines to OS to go through a handler routine, which protect PCB and is sole arbiter of reading and writing this block. So basically, first of all, we have PCB is very important. We know that. Okay, why this is important? Because it single-handedly contains all the information about a process. Okay, so these information are very sophisticated. The difficulty is not access but protection. So using accessing a PCB is easy. Okay, we can actually just request a process and then we can access the PCB. But the problem is, one PCB must be protected from another PCB. That means if there is a virus in your computer, it must be protected. Then these problems, how to solve this problem? We solve these problems by actually addressing a routine or a program to go through all a handler. So that means every process we have will go through a handler. And what is the task of that handler? It will protect the PCB and will be sole arbiter for reading and writing. So it will only able to read and write. Other processes will not be able to write the blocks. So these are the rules for PCB. And there are two modes. We have already covered this: user mode, system mode. User mode means you can actually do whatever the this operating system and other process allows you to do, and system mode means you can do whatever you want. Okay, so your system mode is more powerful. So sometimes what happens that whenever the typical operating system have these functions, in process management it creates process, in schedule process, dispatch process, and so on. Memory management, it allocates memory, swap. IO management, buffer management. Support functions are interrupt handling, accounting, monitoring. So these are the functions in the kernel. Okay, now what happens sometimes whenever you are creating a process, okay, since system interrupt occurs and you actually have to handle that. Okay, and to handle that, okay, sometimes you need the permission of the system. So if you're let's assume you have a, I think you have all seen it, that if you suppose you actually have installed a new software in your computer, and suddenly from that new software it is asking for you to permission to access the network devices. So in that case, okay, whenever it's asking the permission from the network devices, so what happens is that you have to first give it the permission that you can access the information, and then you can actually load the information. So these are the steps for creating the process. So we have discussed these steps of how to create the process. It assigns the process identifier, allocates space, initialize the process control block, sets the appropriate linkages, okay, and finally expands the PCB data structure. And so we have, I think we are done with this chapter. Oh, this one is remaining. So these are actually the steps on a full process switch. So initially what this is actually have been discussed in lecture 2, but let's go again. So first, okay, we are trying to actually change the process state. So let's assume a process in a running state, we want to make it to the block state, or in the block state we're going to the ready state. So we have studied that there are different states of a process. So the question is that we have this different states of the process. So we can send one process from running to ready, ready to running, running to waiting, and so on. So the question is that if you want to actually switch a process from one state to another state, what are the operations that you need to do? So these are the steps. Here, as we can see, there are 7 steps. Step number 1, you save the context of the process. So everything that you are doing, okay, you first save it, okay, so that you don't lose any information. You update the process control block PCB with currently in the running state. So you have to update the information in the PCB as well. Then you move the process control block of this process to the appropriate queue. So after actually saving the context and saving all the information in the PCB, you actually move back to the queue. So if you're actually waiting for other processes, let's assume there are 3 processes that are waiting. So let's assume this is the line. So this is the process number 2, process number 4, okay, and this is in the CPU. Okay, so this is actually, let's assume this is my CPU, and in the CPU I am currently executing process 3. Okay, now suddenly process 3 will be changed CPU to the, again it will actually go to another state. So what we will do, we will first save the context that we have to save process 3. After that we'll update the information in the PCB, okay, and after that we'll actually move it back to the last of the queue. So let me draw it again. So it will actually go here, okay, and then this CPU will be empty, all the information is stored, and then what we will do, select another process for execution. So from the queue that we have here, process 2 or 4, okay, we'll either select process 4 or process 2. This might depend on the priority, that which process have higher priority. This might depend on the serial, that which came first, and many other. Then update the process control block of the process selected. So then if I select, let's assume if I select process 4, okay, then I will update the information of the PCB. So all the information of the PCB will be updated, and then finally we'll update the memory management, and finally we restore the context. So the very simple steps. First, we want to switch, let's assume a process A. So first we have to save the context of process A. We have to update all the PCB information so that we don't lose any information. Then we have to move it to the back of the queue, that you go back to the line, end of the line. Okay, then you have to select another process. Okay, after selecting the process, you have to again load the information, update the PCB, update the memory management and data structure with the new process. So if I actually, so this was save A, update PCB of A, okay, move A. So these 3 steps was all about A. Then this is the selection step. Okay, select. So we select the new process, and let's assume we have selected process B. So we'll upload with process B. the PCB will save memory with the data of process B, and finally will restore the context of process B. So maybe it happened that process B was what you are working with PCB before, okay, process B before, so all the information will be updated. So that's how actually the process switch takes place. So we are actually done with this chapter. So if you have any confusion,